Section 3, Absolute Value Equations and Inequalities. Well, let's review a little bit what absolute value means. The following is a formal definition of absolute value. They start putting squares and coloring things in a book. That means they're important. So, absolute value of x denoted by the straight lines on each side of x here, these bars here, or pipe symbols sometimes they're called. We use those in the set builder notation for such as or such that, right? Well, both of them means absolute value. So if I have the absolute value of x, there's two things that happen. One is x, it is actually the value x if x is greater than 0. And it's a negative or opposite of x if x is less than 0. So when x is non-negative, the absolute value is x. When x is negative, the absolute value of the absolute value of x is the opposite of x. Now, the best definition I've ever heard for absolute value is distance from 0. So I have a negative 5, that is 5 away from 0. Or if I have 5, that's 5 away from 0. But we're going to have to get into really realizing what that means, since we've covered inequalities. We're going to show it in an algebraic language, right? And a lot of what we do is translate English into algebra so we can solve more complex problems. And that's kind of what they go through in this first one. It says, since distance is always non-negative, we can think of the number's absolute value as the distance from 0 on a number line. Okay, so they kind of show it right before the example. I kind of like this as, that they highlight this definition a little bit more, because if you remember that, usually errors that occur from thinking that absolute value is the opposite of something is stopped usually. So, or you don't have those errors. Well, let's look at what happens if we have an equation with absolute value. Here's a real simple one. The absolute value of x equals 4. Now what that means is x is 4 units from 0, and we have two places that it occurs on the number line, at negative 4, which is 4 places away from 0, and at positive 4. So, and then we also would interpret the absolute value equal to 0, absolute value of x, then would be it's 0 away from 0, or it is actually the number 0. Now, the absolute value principle for equations, for any positive p, number p, and any algebraic expression x, notice that they go into these capital letters usually when they're saying, hey, this variable probably will represent some more complex expression. The solution of the absolute value of x equals p are those numbers that satisfy this condition. Well, x will be equal to the negative of p, or x will be equal to p. So the equation absolute value of x equals 0 is 0. And also this is important, is the equation, if we have the absolute value of something, some expression equal to a negative constant, that is not possible. So let's look at some of these more complex ones. So with this principle, this A part of this, these principles they're putting down here, the A part is that we have the absolute value, like this first example, is the absolute value of 2x plus 5 equals 13. Well, to kind of define this, they say, well, this 2x plus 5 will be the x in that principle they were talking about, and p is the 13 in this case. Well, when we apply this deal, we get rid of the absolute value symbol by making this expression equal to the opposite of this, or, and it's an or statement, it's a union, 2x plus 5, we got rid of the absolute value symbols, is equal to the positive one, or exactly that. Now we have two equations to solve. They get x is equal to negative 9 or x is equal to 4. And then we should check that. I mean, we should go in here and say basically we have two solutions, we have two things to check to see if it works. So I'd go back to the original right here, and I'd put in negative 9 in for x, and I'll get 2 times negative 9, which is a negative 18, plus 5 is a negative 13. The absolute value in negative 13 is 13. So that makes it true, right? And in this case, I substitute in 4. I get 2 times 4 plus 5. You end up with the absolute value of 13 is that equal to 13. So those are the two solutions. By using this principle, I can break this, or I deal with the absolute value symbols in this way, is I can take it and make a union of two equations with no absolute value symbol. So the absolute value here they're going to look at, what if I have something a little more complex and when I'm trying to solve these things? Well, this is not a parentheses. You got to remember absolute values is a whole different ball game than just a grouping symbol. Well, when I have this function f of x equals 2 times the absolute value of x plus 3 plus 1, we find all x for which f of x is equal to 15. So in other words, I put in for f of x 15, and that's what they show here. So here is something I can solve for x. Well, what I need to do is solve for the absolute value. I need to get it down to the absolute value, and then I can apply that principle and separate into two different equations and get rid of the absolute value. I cannot do that until I got just the absolute value on one side of the equal sign, right? So what they do here is they add a negative 1 to both sides and they get this one, and then they take 1/2 times both sides. They say divide by 2, which is the same thing. And now I just have the absolute value of x plus 3 is equal to 7. Well, for this to be true, x plus 3 could be equal to negative 7, or x plus 3 can be equal to 7. So I solve those two equations, I end up with two solutions, and then I check that. I'd put it back and then into the original, and if I did 4, I'd end up with 4. Now when you put values in, you remember this works like a grouping symbol, but I can actually do the addition inside the absolute value, and I get 4 for x here. I get 4 plus 3 is 7. 2 times 7, well, the absolute value of 7 is 7, right? I can do that. 2 times 7 is 14 plus 1 is 15. That works. Same would work with negative 10. Now this one here is pretty much the same, and they're saying because of this form, and you have to think about a couple things here, is it can be solved in two ways, and let's look at this. Method 1, we could interpret the absolute value of x minus 2 equals 3 as stating that the number x minus 2 is 3 units from 0. Using the absolute value principle, we end up with x being this and p being that, right? Well, they create two equations, right? And they get x is negative 1 or x is equal to 5. Now, the expression, what they want you to see here is the expression a minus b and b minus a both represent the distance between A and B on a number line. For example, the distance between 7 and 8 could be given as the absolute value of 8 minus 7, right, which is 1. And you'd get the absolute value of 1 is 1. Or it could be as 7 minus 8, right, which is a negative 1. The absolute value of negative 1 is doing that. So from this viewpoint, the equation x minus 2 equals 3 states the distance between x and 2 is 3 units. Okay? We can draw on a number line and locate the 3 units from 2. So I could go in here in 2 and say, well, 3 units from here is negative 1 to the left, and 3 units is 2 is here. And basically I could pull out a solution just by thinking of how absolute value works on distances, okay, and distance on a number line. On simple expressions like that, boy, that'd be handy rather than have to solve and do all those kinds of things. So I need to check that. I end up with negative 1 and 5 are possible solutions. I check those and find out. Okay. So some equations contain two absolute value expressions. Consider this absolute value of A equals absolute value of B, and so on. Well, here are the any algebraic expressions x and y. Remember, the capital letters are usually talking about expressions. It says if the absolute value of this expression x is equal to the absolute value of this other expression y, then x is equal to y, or x is equal to negative y. Looks pretty close to that same principle we've been working with, right? So when we get a problem like this, where I have the absolute value of 2x minus 3 equals the absolute value of 5, x plus 5, I can create two equations. Assume that the two of them are the same. I just get rid of the absolute value symbols. I get 2x minus 3 equals x plus 5. Solve that, I get x equals 8. But if I assume that this is equal to the opposite of the other one, then I take the negative of that, make sure you distribute that negative, and I get this right here. Solve that and I get x equals negative 2/3. So what I think is the solution to this is 8 and negative 2/3. I can put it back in the original and check and see. That'll work in this case. Now inequalities kind of throw another couple of curves into this absolute value scenarios, right? Let's look at a couple of examples again here, and they're going to show us a couple things that can happen and or always happen, really. And so the first one they're going to look at here is when we have a less than. So we have the absolute value of x is less than some number, in this case 4. And if I think about this graphically, they kind of show the graph already, but if I think about this graphically, it means I got a narrow set basically close to 0 in some way, or associated with 0, that to make this true. And what they want you to see is, remember when we were talking about the AND or the intersection stuff, we could end up with this abbreviated method, or basically there is an end on both ends of this things, and there's still an infinity of solutions in this case, but there's a beginning and an end on this graph. In this case, we end up going here. Now let's read this. It says solution of absolute value of x is less than 4 are numbers whose distance from 0. So you think about that distance from 0 thing again. And I would do that. It would mean everything up to, right up to negative 4. If I put negative 4 in there, it doesn't work. But everything to the right of negative 4. And then I'd go from 0 up here, I'd go to 4, and it's everything left of 4. Well, both of these have to be true in a sense, or it's an intersection between you know, in this case where I said x is greater than negative 4, and on this deal, if I went this way, x is less than 4. Well, it is the intersection of those that make this true. Okay, so we end up with an abbreviated method here. Here's the graphing, here's the interval notation. Okay. When I end up with greater than with absolute values, and I still think about this distance from 0 stuff, for the absolute value of x to be greater than or equal to 4, I would, you know, at first, if you're not quite sure what's going on here, just start plotting some points and test. I put 0 as an easy one to start with. I put 0 in there. Is 0 greater than or equal to 4? No. And you'll start seeing, hey, I got to get right of or use 4. 4 works. If I put 4 in here because of the equals part, absolute value of 4 is greater than or equal to 4. Yeah, that's true. I could put 5, 6, 7, 8, 3022. All those could go in there and make that true. So it's everything right of and including 4. Well, what about on the other side? Same thing when I get to negative 4. That actually works. The absolute value of negative 4 is greater than or equal to 4. Well, it continues on too. If I take negative 5, negative 7, so on. The absolute value of negative 7 is 7. 7 is greater than or equal to 4, and so on. So I could go off here into the negative thousands and it would still work. Completely kind of different type of scenario. And what we're talking about now, notice this union symbol, where in the less than we're talking about intersections, and here we're talking about unions. So they give these principles on absolute values too. It says for any positive p and any expression x, remember that large number represents some more complex expression. The solution to the absolute value of this expression x is equal to p ends up to satisfy these two things. Notice there's an or. It includes both of these things. And that's where we got the two equations to solve. Now, solutions in the inequalities, if it is less than some expression less than some number, we end up with that number's itself and its opposites being borders to this thing. So I'd go negative p as my left side of this thing, and positive p in a graph would do that. And then I can represent it that way too. If there's a greater than symbol, we end up with an or situation. This actually really is an intersection scenario with less than. In this case, I go with the solution here. It says this expression will be less than negative p, or p is less than x, or I could say x is greater than p. Okay? Or in other words, my expression is greater than the positive version of that and less than the negative version of it, because when I hit the positives, I'm going to end up with everything to the right of that is greater than. When I get to the negatives, everything left of that will work. Okay. Now they're going to get into some concept stuff here. Graphs are very nice things to look at with absolute value. They show two graphs here. F of x equals an absolute value of x. That's this red graph here. And if you think about that, if I put this point in here, if I had 3 for x, right, I'd get the absolute value of 3 for f of x, which is going to end up be 0.33. Well, the same thing if x is negative 3, I end up with a positive 3 for f of x, and so on. Here I got 0.11, negative 1, 1, so on. So we end up with these V-type graphs. Now g of x equals 3 is, I see so many errors around when it's equal to a constant. you think about that. If I put in a value for x, any value for x, my g of x will be what? It'll be 3. In other words, it has to be a line where the f of x value, or in this y-axis, the ordered pair, the y coordinate is always 3. Well, the only way that happens is you have a horizontal line. Okay. So where the graphs intersect, they're showing these 2 points of negative 3, 3 and 3, 3. The graph of this would be absolute value equals 3, right? Where the graph lies below this graph is the absolute value is less than 3. And where the graph lies above this line, this dividing line, we get the absolute value is greater than 3. Okay. So using graphs above to match each equation or inequality to its solution set, we can see some patterns, and they show you that, where you can just kind of do a matching there. It's a good little exercise. Alright, so let's solve some inequalities, where I got the absolute value of 3x minus 2 is less than 4. Big deal whether it's less than or greater than. We treat them differently. So in this case, we know that we could abbreviate this to be negative 4 is less than this absolute value portion of the expression, or just the expression, and this expression has to be left of 4. So they go from here and they take that p-value, they put its opposite here and its actual value here. This is an and statement in itself, right? I could also write this as negative 4 is less than 3x minus 2 as a separate deal, and then write a different one as 3x minus 2 and 3x minus 2 is less than 4. Well, if you get used to this notation, I can solve basically both equations at the same time. If I'm working with this 3x minus 2, and if you think about that, when I have this expression I'm trying to get to x, I'm going to do exactly the same steps if these two things were separated. I'm going to add 2 to both sides, and then I'm going to take 1/3 times both sides. Doesn't matter if I had negative 4 is less than 3x minus 2. What are you going to do? I'm going to add 2 to both sides, and I'm going to take 1/3 times both sides. Well, they're just doing it together here. They added 2 to both sides, which means I got to add it to here and to here. Okay? I still treat it like there's two inequalities going on. And then when I take this times 1/3 to get just x, I have to take 1/3 times negative 2 over here and 1/3 times 6. So I end up with this set builder notation of the set of x such that negative 2/3 is less than or left of x on a number line, and x is left of 2 on a number line. They both have to be true in this case to make it represent solutions. Okay. Example 9 here, we have kind of a complex thing in here, and we can talk about this. F of x equals now the absolute value of 4x plus 2. But they want us to find all x for which f of x, or the result of this expression in absolute value, is greater than 6. So in other words, they're taking these two functions where we know they put a condition on that, and basically I build an inequality from that. Since we know that we have to have f of x is greater than 6, well, f of x is really this expression, the absolute value of 4x plus 2, the absolute value, right, is then has to be greater than or equal to 6. Well, with greater than things, we have an or situation, is we have a union situation. So to solve this, we use the principle of taking the opposites and creating two equations. So I can go get rid of the absolute value by saying 4x plus 2 is less than negative 6, or if you think about that, negative 6, what would have to happen? I'd still have to go farther left of negative 6 to get these absolute values bigger than 6, right? And here I got 6 is left of this, or if I flipped it around, 4x plus 2 is greater than 6, or these values in here, to make this absolute value greater than 6, these positive ones have to be on 6 or to the right of 6. You know, I can kind of think about that graphically as distance from 0, right? Distance from 0 has to be true on these greater than things. Well, make sure you get these set up right and then solve. I get, in this case, x is less than or equal to negative 2, or 1 is less than or equal to x, or this, another way to say this, x is greater than or equal to 1. So we end up with a graph like this. Here's your interval. Notice that union statement, or in a set builder notation. So they talk about technology here a little bit on a graphing calculator, which we're not using very much. You go into other math classes, you'll get more into the graphing calculators. So that's it for this lesson, and good luck. Again, remember your goal on all the homework is to get 100%, and you should be able to do that with getting the online help that's there. Use your book. Do that. It can be very frustrating to be doing more and more problems, or practicing doing it the wrong way is not a way to be successful in your testing.